Hello, this is Dr. Heidelberg, and today's presentation will be discussing qualitative principle of operation of finite element analysis. We will look at the basic concepts which are accumulated from various sources, and this presentation shows us that we starting with a physical phenomena of a certain process that we're interested in analyzing, such as related to solid mechanics, fluid mechanics, thermal conductivity, diffusion, electrical conduction, acoustics, etc. And we use the governing basic equations which describe this phenomena in terms of independent variables such as temperature, displacement, pressure, and independent variables such as XYZ as well as time. And we transform the analytical equations into a discretized set of equations, which are so-called finite element equations. And instead of solving a complex differential equation, we are required to solve a more simplified algebraic equations. These process is the basic, and we'll take a look at the more detailed description of it. I'd just like to make a note here that all of these presentations are taken from the various sources which are listed on each one of these pages, and we thank the contributors for their contribution. The process in a little more details started with the fact that physical phenomena are expressed by governing equations which represent the behavioral laws. The behavioral laws may relate to equilibrium, conservation of momentum, conservation of energy. These equations, which describe the behavior as material deformation, fluid flow, and heat transfer, are of course of interest to engineering professionals. These equations relate dependent variables such as deflection, temperature, and pressure to independent variables such as XY positioning in space and time. The mathematical nature of the equations is often nonlinear partial differential equations within an object which is rather complex. The object may often be geometrically highly complex, and these complex equations are many times impossible to solve explicitly. The finite element analysis is an approximation method to solve these complex equations by replacing them with approximate set of algebraic equations for small elements. The approximate equations, which describe the phenomena within a small element, are written as a function of the independent variables, a discrete number of nodes which surround the element. The object is discretized into many finite elements, and then a set of algebraic equations of all the integrated elements, which are assembled together into a single part, are being applied some boundary conditions and initial conditions, and then they are being solved for the numerical values of the unknown variables. The results are then presented pictorially using colorful scale. We can take a look at each one of these steps in a little more pictorial way with some references. So we see that the physical phenomena, which is expressed by governing equation, could be Hooke's law, for example, or various heat transfer relationship which relate temperature and heat flow. We see that the equilibrium, for example, of the continuity equation is shown over here. For example, a fluid flow that is coming into an element and going out of an element must be equal with the fluid flow which is being generated within the element. We see that the equations are representing various parameters, engineering parameters, such as speed, elevation, pressure, density. These are typical commonly used equations. And the principle of finite element analysis is that the equations which relate the deflection temperature and pressure to independent variables like x and y are being expressed analytically in an integral or partial derivative form. We see over here that we have the principle of real work showing that the forces times the displacement of the external environment equals to the integral virtual work within the element, which is the stresses times the strains integrated over the entire volume. We see that the differential equations could be rather complex, as we see over here the Navier-Stokes equations with actually many degrees of freedom in each one of the xy coordinate systems. As we see over here, they get fairly complex. The objects are also many times highly complex, such as a crankshaft or a motorcycle cylinder. We see a complex bevel gear or a gate valve. The principle of solving these complex equations is many times related to numerical solution, like difference equations or finite element analysis equations, and the reason is because the explicit solution is extremely difficult to obtain for nonlinear cases with difficult boundary conditions, and not to mention transient solutions. The approximated method of the finite element analysis is relating in algebraic set of equations the forces, for example, here in a stress analysis case, to the displacement with stiffness matrices. And these forces are vectors in the various nodes values, and over here these are the displacement at various nodes within the elements. The solution is based on the equations which are linearized within each one of these elements. Each element has a certain number of nodes. There are many types of elements. This is a tetrahedral element that has 4 nodes representing a solid object. And each one of the nodes has its own local UVW coordinate system within which we can describe the characteristic of the element, and they all work within a global coordinate system, XYZ. Eventually, they all have to be integrated and assembled into the XYZ coordinate system. But within each element, we see that there is a relationship between the forces and displacement at each one of these nodes. F equals the stiffness times the deflection, and these are vectors are forces at the nodes and deflections at the nodes, and the stiffness for each element in this particular case is made of the characteristics of the element itself, such as the cross-sectional area, the length, and the modulus of elasticity. We see over here also moment of inertia, and this is a representative of an element that has actually three linear and three angular degrees of freedoms. When we come to solve the problem, we have to discretize the element, as complex as it may be, into these finite elements, and then we have to integrate all the individual equations into one unique equation in a global coordinate system that relates all the forces on the right-hand side to the unknown variables on a left-hand side, with the stiffness or any operational matrix for the process that we came up with. And the solution for the system is done after we assign boundary conditions. And when we see here an example of a linear element with its global matrix of stiffness, this is before we apply boundary condition. And then when we apply boundary condition, we set one of these elements to a certain value. For example, the displacement at node 1 is set to 0, therefore we put this element to 0. It eliminates these two row and column, and then we end up with solving these two equations on two unknowns right here. And once we solve for the U2 and U3, we can plug them back in here and solve for the force knowing U1 and U2, because that force F1 is equal to K1, which is known, times U1, and then plus K minus K times U3, and therefore we can solve knowing U1, we can solve for F1 simply as equal to K minus K times U3. We see that the solution for many equations with many unknowns could be rather cumbersome, and the number of equations that we may have to solve is on the order of the number of nodes times the degrees of freedom at each node. A number of nodes could be 30,000 nodes, and degrees of freedom can be 6. So it's extremely important to have fast solution techniques for these equations, and that's what the finite element analysis tools are doing. Once we solve the equations, then the results are shown pictorially with a color that indicates the level of the results with a scale which is given on the side of the finite element analysis. This concludes our presentation, and we will do some lab experiments with simple elements to demonstrate this whole process. Thank you.